This conference will now be recorded.
Very good morning, students. Today we have few interesting things to discuss. Let us try to learn few interesting things. So we were discussing electrostatic and properties of conductor. Yesterday we have learned various properties of conductor, and we had also discussed electric field and potential due to charged spherical cell. This part we had discussed. So I'll just briefly recap, and then I'll go to the remaining topic I could not discuss yesterday's class, that is solid conducting sphere. Okay, so see, when you have a conducting cell, so inside there is no charge. Okay, so you can see the field, electric field inside means at any point r, which is less than capital R. Capital R is the radius of the cell, spherical cell. So electric field will be always be zero according to Gauss's law. Okay, we have proved yesterday. Why? Because Gauss's law says E into S is equal to charge enclosed by Gaussian surface divided by epsilon 0. So if I take a point inside, the cell and draw the Gaussian surface through that point, then this Gaussian surface doesn't include or does not enclose any charge. Therefore, right hand side will be 0 and hence electric field is 0. So this is one point. Second point is that electric field at any point outside the cell. So that is shown over here. See, in this figure it is shown. If I draw a Gaussian surface of radius small r, which is greater than capital R, that is the radius of the spherical cell, then see, applying Gauss's law, we can write ES on the left hand side. This is a flask through the surface, through the Gaussian surface, and this is charged enclosed by epsilon 0. So here, if the cell has charge, total charge Q, then Gaussian surface actually encloses all the charge. So I can write left on the right hand side Q. How about the electric field? Electric field will be always constant at any point, here, 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 here. So I can take that out of integration. So that's how I have written it here. Only thing is this area. So area for a spherical cell is 4 pi r square. Surface area of a spherical cell, 4 pi r square, right? Here actually this area I have to take as take the area of the Gaussian surface. So electric field will be Q by 4 pi epsilon naught into r square. So I'll just write in, okay, so this is the electric field. Okay, I'll just let me write in concise way. So electric field will be Q by 4 pi epsilon naught r square. That means outside the, like at electric field at any point outside the spherical cell will be identical to the electric field produced by a point charge Q. That means what? All the charge, okay, all the charge on the sphere as if sitting on the center, at the center. Okay, so all the charges on the sphere as if sitting at the center as a point charge. Okay, as a point charge, like all the charge on the sphere is sitting like a point charge at the center. Okay, so that's how electric field has variation outside 1 by r square variation, and inside it is 0. So if I have to draw the variation of electric field all the way from center to any point out, any outside point, then how do I draw? You look here. See, this is at the center. Center, what is the value of the electric field? That will be 0. At any point till surface, it will be electric field will be 0. As you can see, up to r is the radius. So till the surface, it will be 0. And beyond the surface or beyond the sphere, we see r is greater than r, capital R, that is the radius of the sphere. So there, the variation will be this. So this is this way. Okay, 1 by r square variation. So this curve is very important. But what is the electric field at the surface? So at the surface it will be maximum, and that is q by 4 pi epsilon naught capital R square. And see, in fact, see this 4 pi capital R square, I can write that, see, q by 4 pi capital R square. This is the area of the spherical cell. So I can write this as area q by area, surface charge by area. I can write as sigma by epsilon 0. This is the surface, like charge outside the surface. Okay, outside any conductor, just outside the conductor, the electric field will be sigma by epsilon 0. This is the property we have already learned, and here also we can see that. So electric field just outside the conductor, electric field will be always sigma by epsilon 0. Okay, so these are few points we have already discussed. So today, see, one more point here we will discuss. Like we have already discussed about electric field. Then how about potential for a cell? See, when electric field is 0, let me tell you here. See, electric field is 0. We know minus dV dr is equal to E. So E is 0. So dV dr or dV will be 0. That means what? At any point inside the surface, inside the spherical cell, suppose 1, V1 minus V2, that is 0. That means what? V1 is equal to V2. See, if I draw this, see, suppose this is inside any point where the potential, like where point 1, this is point 1, and somewhere here this is point 2. So what is the potential difference between these 2 points? That is 0. That means what? V1 is equal to V2. That means what? Everywhere the potential is 0. Sorry, the potential is constant. The same potential you will see inside the spherical cell. So that's why the inner surface of the spherical cell, even so the surface area of a spherical cell is called equipotential surface. And what will be the potential inside? What is the numerical value of that? Numerical value will be exactly equal to the potential on the surface. So what is the potential on the surface? We have seen already, q by 4 pi epsilon naught r. So this will be the value inside and on the surface. But what about electric field outside? See, we have already seen electric field. So electric field will be constant. There will be no space variation inside. So that's why this part up to surface. But outside the surface, so V we have to draw, like we have to find out V at any external point. See, electric field we have already found out. What is that? Q by 4 pi epsilon naught r square. R square. Now dV dr minus dV dr is this, right? So if I want to calculate, see, I have to calculate dV r to r. Sorry, this is dV is V surface to any point outside VR. Okay, and here with the minus sign, q by 4 pi epsilon naught this, so dr by r square, and it will be r2 small r. Okay, so now if we do this integration, see, I'll just do the integration here. This will be actually vr minus vs, and on the right hand side, see, this will be minus 1 by r. Okay, minus 1 by r, so this will be ultimately plus this, and 1 by r, limit will be r to small r. Okay, so you get 1 by small r, 1 by r. Okay, this is on the surface, and this is also on the surface. Okay, so if I can just do one thing. So this is with minus sign vs. Vs is also same as this q by 4 pi epsilon naught r. So this actually can be cancelled from both sides. Okay, so it will be, I'll tell you why I have cancelled this from both sides. So vs is on the surface, q by 4 pi epsilon naught capital R, with a plus sign in this side, and this was 1 by q by 4 pi epsilon naught, this with minus sign. So this will get cancel each other. So I get severe potential at any point outside. So that is varying as 1 by r. So this is the variation, and this is the respective curve. All right, let us go to today's topic, which is very, very interesting again. So electric field and potential due to a solid sphere of charge q, say. First we will draw, like we will calculate electric field. There are 2 points, right? Electric field inside and electric field outside. So let us find out electric field outside first. So this is the Gaussian surface, as you see. If I take this as, I think this is for inner. Okay, let me just calculate for inner part first. Inner point. So this is the Gaussian surface. See, this is first of all solid sphere. So there will be charges throughout the volume of the sphere, throughout the, just like a short football, or orange. Okay, orange, there is matter inside, isn't it? Not a tennis ball. Tennis ball may be hollow inside. Okay, but here it is actually kind of a short football. It has charge throughout inside. So what we have to do, we have to find out electric field inside at any point. See, inside at any point, like any point inside the sphere. And I have, see, because of symmetry, spherical symmetry, I can use Gaussian surface as spherical one. Okay, or sphere. I mean to say, I can apply Gauss's law to calculate electric field. So I have drawn the Gaussian surface as a sphere of radius small r. Now I have to find out the flux through that. So flux through that will be, so E electric field into area 4 pi r square. Okay, r square, r is the radius of the Gaussian surface, small r. Okay, so this part is very fine. Now what about right hand side? This is charge enclosed by Gaussian surface into epsilon 0. Suppose it has total charge q. Is the Gaussian surface encloses the whole charge q? The answer is no. As you can see, this is the Gaussian surface, so the charges inside is much lesser than the whole charge itself. So that means it will be enclosing some of the charges, but what is the amount of that we have to calculate. So charge enclosed, by that we have to find out. How to find out that? First of all, we can find out, see, rho, charge density into the volume of Gaussian surface. This I can do. Gaussian surface, sphere or surface, I can say. Okay. So what is rho? Rho is the total charge by total charge, that is Q, by volume of the whole sphere, that is 4 by 3 pi capital RQ. This capital R is the radius of the sphere. So this is rho. So what about volume of this small sphere, like Gaussian surface, that is 4 by 3 pi small RQ. Okay, so this 4 by 3 pi, this will be cancelled from both sides. So I can write Q RQ divided by capital RQ. Okay, so this is the charge enclosed. Now if I write it here, see E equal to charge enclosed, I have already found out, so I can directly write from here. See, from here charge enclosed is Q RQ by capital RQ, and here see this was there, so 4 pi r square will be in the denominator. 4 pi r, so obviously there will be epsilon 0, so I'll write it here, and this will be small r square. Okay, so look here, this and this, they will cancel each other, and ultimately what we get is QR divided by 4 pi epsilon naught capital R cube. So this is the electric field inside. Okay, this is the electric field inside. Okay, but what is the electric field outside then? So I'll just write one by one. Let me. Okay, so I have got this expression. I hope it is clear to you. I'll just erase this part and I'll write only the final result. So these steps I'm just erasing because I have to do for outer point also, and then we'll compare. So electric field inside will be Q R by 4 pi epsilon naught capital R cube. Okay, now electric field at any point outside, see electric field at any point outside, that is this, we have to write down what it is. So let me just apply. See here also, see in this case I have to draw the Gaussian surface, see like this. Suppose this is the sphere of radius. I'm drawing a small sphere representing the same. So I have to draw the Gaussian surface just outside the outside. Okay, outside, this is R. Now see, I'll write E 4 pi r square is the area of the Gaussian surface. Now what is the charge enclosed here? Charge enclosed by epsilon naught. Here the charge enclosed will be the whole charge. See here, the Gaussian surface is outside the sphere. That means the whole charge is enclosed here by the Gaussian surface. So this will be the result. So what is electric field E? That is Q by 4 pi epsilon naught r square. Okay, so this is except you see here also you can see the result is just like a point charge, just like a point charge. Electric field at any point r, due to a point charge we get Q by 4 pi epsilon naught r square. Here also any outer point, electric field at any outer point due to a sphere, solid sphere, is resembling resembling the point charge itself. Okay, that means as if the whole charge of the sphere is concentrated at the center of the sphere. Okay, so I can write it here. So I'll just write the final formula and I'll erase this part. So electric field outside that is q by 4 pi epsilon naught r square. But what about electric field at the surface? That means when at the surface when small r is equal to capital R, we have to actually, we can use both the formula. Either we can use this formula, write capital R in place of small r, or we can use directly this, in place of small r we will write capital R. So you can see this is q by 4 pi epsilon naught r square, and look, this is just like earlier sigma by epsilon 0, isn't it? Just on the surface or just outside the surface, it is sigma by epsilon 0 anyway. So this is a constant value. So on the surface it is a constant value, or this is actually maximum value. Okay, this has got maximum value. All right, so if I plot all this, look how will be the plot. See here, in this case electric field inside is varying as directly proportional to the distance from the center of the sphere, and for this case outside point electric field is just varying as 1 by r square, just like a point charge. And on the surface anyway this is just constant value or maximum value. So I'll show you how it is. See, the constant or maximum value is this one, maximum value is this one, that is on the surface. Okay, so it is increasing up to, so electric field is increasing up to the center, sorry, up to the surface. Starting from the center of the sphere, electric field is increasing as we go towards the surface, and after the surface it is varying as 1 by r square, it is decreasing as you go away. Okay, so this is how electric field vary. Now, so far so good. It will be very interesting if you see the electric potential. If you see the potential, how it varies and what are the values of electric potential on the surface, inside and outside. See, in case of spherical cell, there was no electric field inside, so it was a constant potential surface. But in case of a solid sphere, electric potential varies point to point. Okay, electric field varies point to point. So we have to now find out the electric potential, how it varies with R. Okay, so see, we have seen electric field at any inside point inside as QR 4 pi epsilon naught R cube. I hope you remember this. Okay, now then what is the potential? What is the potential? So potential will be dV is equal to minus E inside dr. Okay, and how to take the limit? See, we'll be taking limit, integration limit dV. We'll take this as surface to any point outside. Okay, and here it will be r to small r any point, and this is qr by 4 pi epsilon naught dr. Okay, now if we integrate it, what we get, q by 4 pi epsilon naught This is r cube. R cube is fine. So here it is VR minus VS, and this is r cube. See, here it will be r square by 2. Okay, it will be r square by 2, and limit will be small r to capital R. Okay, so what I can write is q by 4 pi epsilon naught r cube. This is capital R square by 2 minus small r square by 2. Okay, now see, we know Vs will be potential q by 4 pi epsilon naught into r. Okay, this is the potential on the surface. All right, so Vs we have got, then Vr will be, see, q by here, q by 4 pi epsilon naught, this one, I'm sorry, this is 4 pi, q by 4 pi epsilon naught r cube, this is r square by 2 minus r square by 2 plus Vs is this one, it is q by 4 pi epsilon naught r. Okay, now look, one thing I'll do here, just a simple substitution, r cube, see, it will be r square by 2 plus, here if I multiply r square both in the numerator and denominator, so this will be r cube, so that I have taken here, so this is r square minus r square by 2. Okay, so this will give you, look here, this is actually 3 by 2, this will give you, I'll write it here itself, this will give you q by 4 pi epsilon naught r cube 3 by 2 r square minus r square by 2. Okay, so this is actually electric field at any point inside. Okay, it is actually the electric field at any point inside. Outside point electric field, calculation of electric field at any point outside is very simple. Okay, so if I place r is equal to smaller, then I'll get it. Look, from here itself I can do it. See, if I place this, sorry, this is on the surface. Okay, this is on the surface. See, if I want to calculate electric field outside, see, from here itself we can do at any point outside. So this will be q by 4 pi epsilon naught small r at any point outside. Okay, this will be the electric field. This will be outside, but inside, finding out inside what electric potential inside is. So this is actually inside, electric potential inside. So what we have got, electric potential V in is equal to q by 4 pi epsilon naught, but obviously we can use this for surface also. R cube 3 by 2 r square by 2. Look in this figure. So I have to see outside, inside, or I'll make the sequence from inside. Let us say center, V at the center of the sphere, V inside at any point inside, V on the surface, okay, surface, and V any point outside. So how they vary? At the center, look what is here. At the center means I have to make r is equal to 0. Okay, make r is equal to 0, then see at r is small r is equal to 0, this will give you, see, this part is 0, right? So you'll get 3q, see, 3q by, see, this will be r square here r, So it will be actually 8 pi epsilon naught just R. So this is the potential at the center. Look here, this is the value. So 3 by 2 q by 4 pi epsilon naught R. So what is the value of this? We'll just see here. See, on the surface we have seen q by 4 pi epsilon naught R. So electric potential is greater. Electric potential is greater at the center compared to the surface. See, the surface value is here, somewhere this value, but at the center it is, see, 1.5 times greater than the value on the surface. So that's why this curve has increased, like here, okay, like this. So at the center or inside, I can say inside the sphere, electric potential will be greater than outside. So we have seen at any point outside we have already calculated, that is q by 4 pi epsilon naught capital R cube, and this is 3 by 2 R square minus R square by 2. This is the value, okay, at any point inside. For the surface we have calculated. For the surface q by, surface means R is equal to R, so you can just put it here. So you'll get q by 4 pi epsilon naught R. At any point outside, you can see, you can actually calculate from the field outside. So it can be directly written actually q by 4 pi epsilon naught R square, sorry, R. Okay, so these are the variation as you see here. So this has got a constant value inside. It isn't actually, it doesn't say, it varies as R square somewhat, but with a negative slope. See, R square, if any, see, this is R, and it is varying as R square. Say any quantity V of R, say it is varying as R square, then I would have written like this, okay, R square means, but it has a negative slope, so it will be like this, okay. Negative slope means it will be like this, so that's why this portion is like this. So electric potential inside is varying as R square with a negative slope, okay, with a negative slope. So that's why inside this is like this, and outside the surface it is 1 by R. So this is actually 1 by R, and here it is actually minus R square. There is just minus R square, okay, with a negative slope. All right, so this was today's discussions on electric field and potential due to a spherical, solid sphere. Now we'll try to take a few more concepts on the potential due to conducting cell. This is very important thing, very important topic in electrostatics, because depending on this concept we will be having like we'll see, we have to come across very important numerical problems, okay. So electric potential due to a conducting spherical cell or charged spherical cell, as you see here. So there are 1, 2 and 3 spherical cells, concentric, as you see, or I can say 2 cells, okay. So concentric cells, okay, and I can just think of radius of this is RA, radius of this is RB, and radius of this is RC, okay. Now what is my motto is that to understand what will be the electric potential at A, at B and at C. So we have to find out electric potential at A, B and C. So to solve this kind of problem, there are few points to remember. So I have to calculate electric potential at A or electric potential at B or electric potential at C. What will be the electric potential at A? I'm writing VA. So what will be that value? See, it is a conducting cell, right? When you have conducting cell, electric potential at any point outside, suppose this is R, and suppose it has charge Q. So suppose this is point P. So Vp will be Q by 4 pi epsilon naught R. Doesn't matter. That's all. But what about this point? Suppose I have to calculate electric potential at this point P. So this is a point P now. And see, this has radius, suppose capital R. The cell has radius capital R, and I have to calculate potential Vp at any point inside. Then what will be the potential? As I said just few minutes back, that for a spherical cell, there is no charge inside, so there will be no field, electric field inside the conductor. So if there is no electric field, so electric potential will be constant everywhere inside. But what will be the value of the electric potential at any point inside? That will be exactly equal to the potential on the surface. Okay, at any point inside the spherical cell, the potential will be same as the potential on the surface. Now look, if I have to write electric potential at A, okay, electric potential at A. So electric potential at A will not be just due to this QA charge. It will be due to the QB charge, or a cell with QB charge, cell with QC charge also. So see, this A point is just on the surface due to Q charge. This spherical cell, inner spherical cell with charge QA, this is just on the surface. I can write it QA by 4 pi epsilon naught RA. If this is the area, RA is the radius of the spherical cell. Now see, this A point is inner point due to this B. I'm sorry, not B. For the spherical conductor, spherical cell having charge QB, or for this cell, the A point is inner point. Therefore, I have to write QB by 4 pi epsilon naught RB. Why? Because the potential due to this QB, like cell with charge QB, will be exactly equal to the potential on its surface, because this A point is inner point to this cell. Similarly, due to the cell having charge QC, it will produce electric potential at A as inner point, that is RC here. Okay. Now if I want to write potential, electric potential at B point, look at B point. I hope this is clear. Radius for this is RA, this is RB, and this is RC. Okay, so B point is inner point to this, like outer cell, and for A it is outer point, so I can write QA by 4 pi epsilon naught. You have to write this distance, okay, this distance, because this is the outer point, so RB you have to write. Due to this QB charge, it is on the surface, 4 pi epsilon naught RB. But for this conducting cell, outer conducting cell, it is inner point. So I have to write QC by 4 pi epsilon naught RC. Okay. The interesting point is this one, VC, electric potential at this point C. This will be C for this cell, and this cell it will be outer point, and for the outermost cell it will be on the surface. So QA by 4 pi epsilon naught RC, QB by 4 pi epsilon naught RC plus QC by 4 pi epsilon naught RC. Okay, so that means this will be due to QA plus QB. Oh, I'm sorry. Yes, this is fine. QB plus QC divided by 4 pi epsilon naught RC. Okay, this is the answer. Okay, so this is one important concept. Now we'll just calculate, like we'll just solve our numerical problem based on this concept. Okay, see, I have to calculate electric potential at P. Look here. So this point P is outer point to this and this. So VP will be, see, this Q by 4 pi epsilon naught. What is this distance? I have to write R only. What about this one? This is minus 2Q by 4 pi epsilon naught. For this also it is outer point. I have to write R. What about this one? 3Q. This is inner point. So I have to write 3Q by 4 pi epsilon naught into 3R, radius of the cell itself. So if I just simplify a little bit, so this is, see, this is actually 4 pi epsilon naught. This will be minus, so Q by 4 pi epsilon naught. This is fine, and so this will be this will be plus. So 3, okay, 3 gets cancelled actually from here. So 1 by R. This will be with a positive sign, and this will be with negative sign. So this is the value. Okay, so this is the value of electric potential at P due to all the metal spherical, conducting spherical cell. Okay, now I'll take up one more problem. See, figure shows two conducting thin concentric cells of radii R and 3R. You can see that this is one conducting cell, another conducting cell having radius 3R. The outer cell carries a charge, this Q. Inner cell is neutral. Find the charge that flow from inner cell to the earth as the switch S is closed. So you can see when this inner, see, this is closing S means you are earthing the inner spherical cell. This is initially neutral, but this has charge. This has got charge. So when you are like making earthing, this is called earthing. When the inner cell is earthed, then the potential on the inner cell will be 0. So that is the fundamental point. Let us say Q prime has got transferred to S. That means just when it was connected, there was Q prime charge on it. So what will be the potential on this surface at any point on this surface? So that I can find out from here. See, potential is, this will be Q prime by 4 pi epsilon naught R, this is on the surface, and for the outer spherical shell it will be 4 pi epsilon naught into 3R, because it is inner point corresponding to that. Now look, when it is R, when the inner shell is arced, the potential, okay, let me write the potential on the surface, potential on the inner shell, VR will be 0. Okay, VR will be equal to 0. So now if we put 0 here, see, we'll do the calculation. If we put 0 here, then Q prime will be minus Q into 4 pi epsilon naught small r divided by 3 into 4 pi epsilon naught r. So this is getting cancelled. So I get Q prime is equal to minus Q by 3. That means how much charge? It is Q by 3 charge, which is flowing from the inner shell to the earth. How much? Q by 3. So this is fundamental idea to solve this kind of problem. Okay, so we'll stop it here for today. Next day we'll start electricity part. Electricity, or sorry, we'll actually we'll do next class capacitor. Capacitor. Okay. Okay, so thank you for your patience. Bye for today.